This afternoon, Professor Zilberstein will present his lecture entitled, AI Will Change Everything, but Not So Fast. Many of the advances in artificial intelligence that are rapidly changing how we perceive and engage with the world were pioneered over the last several decades right here on this campus, and they played a large part in the international prominence of what has now grown to become the College of Information and Computer Sciences. It's particularly fitting, therefore, to have Professor Zilberstein address us on this topic today. Before we invite Professor Zilberstein to present his lecture, I'd like to invite Dean Laura Haas of the College of Information and Computer Sciences to the podium to introduce our distinguished lecturer. Dean Haas.
It's my great pleasure to get to introduce Shlomo today. Shlomo Zilberstein is Professor and Associate Dean for Research and Engagement in the College of Information and Computer Sciences. He works on automated decision-making under uncertainty. How can intelligent systems make good decisions when there isn't enough time to gather all the relevant information and compute the best possible decision? That's a challenge in pretty much every practical application of AI. Shlomo obtained his bachelor's degree from the Technion Israel Institute of Technology, receiving an award from the President of Israel for his work on national security after his graduation. He earned his PhD at UC Berkeley. He has made many contributions to AI over the years. In particular, his work laid the foundation for building what we call bounded rational agents, agents that can cope with uncertainty, with limited information and limited computational resources. Among his contributions are general purpose techniques for constructing well-behaved anytime planning algorithms. Anytime algorithms are algorithms that can be interrupted at any time and still return a valid result. Other contributions of Shlomo's include the first approach for building complex applications from a collection of anytime modules, the concept of a contract algorithm, which unlike an anytime algorithm must declare a running time in advance, and a range of meta-reasoning techniques to manage the execution of anytime algorithms. Starting in the year 2000, Shlomo and his collaborators were the first to identify the fundamental theoretical differences between centralized and decentralized decision-making. They were the first to establish the complexity of the problem and the first to introduce algorithms for solving these problems. Decentralized Markov decision processes have become the standard for decision-making that involves multiple agents. And in fact, just this week we learned that Shlomo and 3 colleagues, including Neil Immerman of our faculty, have just won the IFAAMAS, that's a mouthful, 2019 Influential Paper Award in Autonomous Agents and Multi-Agent Systems for 2 of their early papers on this work. Shlomo has contributed to numerous other facets of AI, including generalized planning, aimed at synthesizing plans that include branches and loops and can handle many different scenarios rather than a single scenario. Stochastic planning algorithms that combine heuristic search and dynamic programming to reduce planning time, and introspective autonomy, allowing autonomous systems to model and learn their own competence from human feedback. He has worked with federal agencies and industrial research labs on translating his research to practical applications. Those range from autonomous planetary rovers to self-driving cars. He currently works with faculty members across campus to develop ways to understand and mitigate some of the risks associated with the deployment of artificially intelligent systems. His contributions are highly cited and recognized by numerous Best Paper Awards at leading AI venues. 4 of Shlomo's doctoral students received prestigious Best Dissertation Awards. He was elected Fellow of the Association for the Advancement of Artificial Intelligence in 2011, and he received the AAAI Distinguished Service Award earlier this year for his extraordinary service to the AI community. Please welcome Professor Shlomo Zilberstein.
afternoon. Thank you, Laura, for this generous introduction, and thank you, Farshid, for welcoming everybody. I'm overwhelmed by the crowd here. Thank you for coming. I'm deeply honored to be here today to deliver this talk, and would like to thank the Chancellor and the Provost for sponsoring this lecture series. This is a great opportunity to pause and reflect on the quest for AI and my work in this fascinating young field. I've been fortunate to launch my academic career here at UMass Amherst and worked with some of the greatest minds that shaped the field of AI, both faculty and students. I want to thank distinguished Professor Emeritus Victor Lesser, who has been a close colleague, mentor, and friend over these years, and my students, both past and present, who played key roles in the research I will describe. I want to thank my family, particularly Karen, for the unwavering support over my entire career. And again, thank you everyone for coming and taking the time and coming to this lecture. The quest for AI is an ambitious project to unravel the enigma of human intelligence and build machines that can replicate it. It is an interdisciplinary field rooted in computational science, but deeply connected with cognitive science, psychology, social science, neuroscience, and philosophy, and physics, of course. If we have learned one definitive lesson from decades of AI research, it is that surpassing human intelligence is within our reach in structured, highly structured environments such as chess or Go. But matching human abilities is extremely difficult when performing mundane tasks in unstructured domains, such as doing laundry. In this clip, created by my former student, Sidor Srivastava, a robot is not programmed to do laundry, but is figuring out how to do it using a high-level description of the actions available to it, such as open, close, pick and place, and so on. The best AI technology in this area is too expensive and totally unreliable. And don't ask about replacing pillowcases. Mechanizing intelligence has a long history, and I will just mention a couple of milestones. Aristotle created syllogism to codify correct thinking, and in the 17th century, Hobbes suggested that thinking is perhaps a computational process. Leibniz invented the binary numeral system and envisioned the universal calculus of reasoning. And the founders of AI created programs that could perform simple reasoning tasks in the 1950s. The famous British mathematician and AI pioneer Alan Turing wrote a seminal paper in 1950 where he said, "I believe that at the end of the century, general educated opinion will have altered so much that one will be able to speak of machines thinking." And he suggested that the questions of whether machines can think is too vague, and introduced what he called the imitation game, or what's called now the Turing test, as a practical approximation. Turing anticipated in that paper many of the principled objections against the possibility of creating thinking machines, and he responded to them in a very convincing way that is very relevant today. But AI is not just about thinking. AI is more about taking action and accomplishing tasks. Not all intelligent behavior is mediated by logical deliberation. So the question that I grapple with, as Laura indicated, is how can we build agents that simply do the right thing, even when they don't have all the information that is necessary, and even when they don't have all the time to think and analyze the situation? It's a challenge that we return to in a couple of minutes. AI as an academic discipline was formed at a workshop in the summer of 1956, organized by John McCarthy, Marvin Minsky, and others. Not our own Provost John McCarthy, the other John McCarthy. They gathered to study the conjecture that every aspect of learning and any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. The organizer of the workshop proposed to find how to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. And they said in their proposals, we think that a significant advance can be made in one or more of these questions if a group of scientists work on it together for a summer, over a summer. Yeah. They didn't make that much progress that summer, but they called the new field artificial intelligence, and they identified a couple of fruitful research directions. At the Dartmouth workshop, many participants predicted that a machine as intelligent as a human being would exist in no more than a generation. And they were given millions of dollars to pursue that vision during what became the first golden age of AI. In 1965, Herbert Simon said, "Machine will be capable within 20 years of doing any work a man can do." And in 1970, Marvin Minsky said, "Within 3 to 8 years, we will have a machine with the general intelligence of an average human being." While progress was very impressive, these claims were exaggerated, and the disappointment that followed led to 2 AI winters, the first between 1974 to 1980, when AI saw a resurgence thanks to the development of expert systems and knowledge-based systems. Another winter between 1987 and 1993, the year I started my career here as an assistant professor. Fortunately, it ended then. There has been tremendous progress in AI in recent years, but the pattern of wild predictions continued. In 2012, Sergey Brin, the co-founder of Google, said that Google will have autonomous cars available for the general public within 5 years. We know now that that problem is a lot more complicated. And the exaggerated claims were followed by equally exaggerated warnings. In 2014, Stephen Hawking said that the development of full artificial intelligence could spell the end of the human race, and Elon Musk said artificial intelligence is our biggest existential threat. These exaggerated claims and the exaggerated warnings are both misplaced, and we will revisit them towards the end of the talk. Now I want to switch gears and talk about my own research on automated planning. Automated planning is concerned with a fundamental question. How can an agent, an autonomous agent, situated in an environment, choose actions intelligently in order to achieve some assigned goals? The idea is not to program the agent to do any one thing, but to give it some high-level descriptions, symbolic descriptions of the available actions. These actions can be described in any number of languages, but they basically say what are the preconditions for performing an action and what might happen when you perform a particular action in the real world. The problem is called plan synthesis. And this general setting is we have a robot, perhaps it needs to clean a room or to perform another task, and it can take any number of actions, and it needs to reason about these actions and form plans. The actions change the environment, and after each action there may be some feedback provided to the agent. The actions can be deterministic or stochastic. A deterministic action has only one intended outcome, and it always happens that way. And stochastic actions can have multiple outcomes, including unintended consequences and failure. The agents can operate alone, or it can collaborate with multiple other agents. And the overall planning process can be centralized, where a centralized authority tells everybody what to do, or it can be decentralized, where each agent needs to figure out what they need to do. The environment can be static or dynamic. In a static environment, nothing happens except if the agent takes action. But in a dynamic environment, a lot of things can happen while you're thinking. And the feedback could be noisy or perfect, or it can be partial in terms of not seeing maybe beyond a certain distance or what's in the next door room and so on. As you can probably figure out, the blue labels represent the more basic and simple version of the problem, and it is sometimes called classical planning. Work on classical planning started in the 1970s. And the red or maroon labels represent harder versions of these problems, and much of my work is focused on the red labels, how to deal with extensions of classical planning, to deal with the complexity that we see in real-world applications. In the rest of the talk, I will talk about some of these contributions. First, I want to talk a little bit about how much thinking needs to take place before acting. Should an agent always try to figure out the best possible action? The problem is that agents cannot think until they find the best action. It may take too much time. They must react to a situation within an acceptable amount of time. The acceptable amount of time may be a few milliseconds, or it could be a few seconds, or it could be even more time. But you want your search engine to give you an answer within a couple of seconds, otherwise you will just switch gears and do something else. Thinking delays action and reduces its value. And we need to deal with uncertainty, and we need to deal with the fact that there is a limited horizon beyond which we may not be able to analyze the consequences of the plan. The conclusion of all this is the appropriate level of deliberation, the amount of effort, is really situation dependent. This challenge was identified by AI pioneer Herb Simon as early as 1956. And he said that the theory of rationality, and he was not talking just about AI, he was also studying human intelligence, so he felt that it's equally applicable. A theory of rationality that does not give an account of problem solving in the face of complexity is sadly incomplete. It can be seriously misleading by providing solutions that are without operational significance. Simply put, what he was saying is that you need to take the cost of decision-making into the decision-making process itself. Simon said that it appears probable that however adaptive the behavior of organisms in learning and choice situations, this adaptiveness falls far short of the ideal maximizing postulated in economic theory. Evidently, organisms adapt well enough to satisfy. They do not, in general, optimize. So he coined the term satisficing, that is simply the Scottish word for satisfying, to denote decision-making that searches until a good enough solution is found, a solution that meets what he called the agent's aspiration level criterion, that was a term borrowed from psychology. So some of the early work I did was grappling with the question, that all sounds good enough, but what does it mean exactly? And is satisficing more than a vague principle? What is a good enough solution, and how can a computer determine that a solution is good enough? What does it mean to be rational when all you can do is satisficing? I realized that you can achieve satisficing in a computational way using lots of different ways. It can be accomplished by design, where the designer of the system determines how much thinking needs to take place and what is the aspiration level. But maybe more interestingly, it can be determined at runtime, when the system actually operates, by the agent itself. And it can also be learned over time using adaptation, based on feedback and experience. That's probably what people do most of the time. They realize how much time they need to spend on a problem based on experience, because last time they probably spent too much, or maybe too little, and they want to correct that. So in practice, it could be a combination of all three. My work is focused on computational models that allow an agent to determine by itself the appropriate level of thinking via self-monitoring and meta-reasoning. Meta-reasoning is simply thinking about thinking. It's the process, or it's sometimes called metacognition, where you reflect on what you're doing and whether it's fruitful and whether you have enough knowledge to solve the problem, whether the method you're using is progressing, whether you need to try something else. All that is a form of meta-reasoning. And we developed similar techniques that work in the context of planning and agent reasoning. So the doing level is the execution architecture of a robot or another system. It simply takes the action and knows how to perform them in the real world. Thinking is the process of deriving the plan or the next action. You don't always need to derive complete plans. And meta-reasoning is the process that controls and monitors the thinking process. And the main idea is to shift the attention from and treat computations as actions. Now, not every addition and subtraction, but really chunks of computations that perform important part of the decision, implement important parts of the decision process. And it's a shift from computing the best action to controlling your planning process or deliberation process in the best possible way to produce good action. We define the bounded rational agent as an agent that performs optimal meta-reasoning instead of optimal reasoning. Now, you may ask yourself, why is that problem any easier? I already told you we can't make perfect decisions. Now we're going to take into account the cost of decision making and make the problem perhaps bigger and more complicated. Why is that easier? Well, it's easier if it's structured in a certain way. And I'll give you a simple example. Laura mentioned anytime algorithms. And in fact, anytime algorithms have this ability to produce not one correct answer for a problem, but many possible answers that improve over time. If you can spend more time, they improve, and they can improve along different dimensions. You may be more certain that the answer is correct, or it may be more precise, or it may be more detailed, or in general, it may be more effective when you execute it in the real world. So if a traditional algorithm works for some extended period of time, maybe an unacceptable amount of time, and gives you the right answer to a problem, an anytime algorithm that is shown by the intrinsic value graph gives you lots of different solutions that improve over time in their quality. The intrinsic value represents that quality. But there is cost to delaying action, and that is the cost of time. The cost of time can be represented using different functions, but usually there is a marginal growth in the cost of time. Perhaps initially it's okay to take a couple of seconds, but after that it becomes less desirable, and at one point it's unacceptable. When you combine the two red lines, you can get a comprehensive value, and that graph may have a particular point at which you should stop thinking and take action. And in this case, it's a single point where, at that point, the cost of thinking outweighs the benefit. We try to develop that in the context of different planning algorithms, and I'll give you a simple example of an anytime algorithm for a problem that perhaps you can relate to. The traveling salesman problem is a well-known problem in mathematics and operations research and computer science. It's an abstraction for a wide range of practical combinatorial optimization problems, and there's been a lot of work on solving it efficiently. It's a hard computational problem. What you need to do is very simple: to visit n given cities and return to the place where you started. And finding the shortest path for doing that is one of those what's called NP hard problem. It's a hard computational problem. So here's an example of an anytime algorithm that can do that. You can generate an initial tour or path very quickly using any particular technique. For example, an algorithm that always visits next the nearest city and quickly visits all the cities. A computer can compute that in a fraction of a second. At that point, you can start improving it gradually, and you get a sequence of solutions that improve over time. One way to do it is to just choose any random two edges, and consider visiting their endpoints in a different order. And if the blue lines end up being shorter than the red lines, you simply replace the red lines with the blue lines, and you get the shorter tour on the right. And if you continue to do that repeatedly, you get an algorithm that, with some tweaks, can actually give you very good answers very quickly. It doesn't guarantee optimality, and it may not actually converge on the optimal answer, but it does give you very quickly good answers. There are many other algorithms for solving TSPs that provide good approximations. The problem is that if you want to spend a certain amount of time, you're not always sure. It's not like a deterministic fixed graph. There is uncertainty on how much progress you will make. That's the nature of most of AI techniques that are based on search, is that you can't be sure what will be the quality of the solution. So meta-reasoning needs to take that into account. Another problem is that many systems are not going to be built from one algorithm. They're going to be composed of many components, and maybe some of those will be anytime algorithms, and that presents yet another meta-reasoning problem. So in this line of work, we looked at a whole variety of various meta-reasoning problems, where the main idea is to introduce certain trade-offs into the design of the algorithm, and then ask yourself, what is the best way to control this trade-off in a particular context, in a particular situation? The main idea that is kind of connecting all these techniques is treating computations as actions in another space, and valuing or estimating the value of computation using information theoretic measures. Because computation answers a question and provides some useful information. And that information has a value. The value is derived from how it can improve your solution or the expected improvement. Next, I want to talk about the fact that you don't need to do all thinking first and then act. There are other designs that proved useful, and there are different meta-reasoning questions that arise in that context. In this particular case, I'm showing just 4 examples. The black part is the planning part, and the blue part is taking the plan and executing it. So if a robot is assigned a task, first it may need to plan how to do it, for example, deliver a package across campus, and then it will need to execute that plan and deliver the package. And the top example shows you maybe an optimal planner that gives you the best plan and then executes it. There's a certain completion time. An alternative is to do approximate planning that gets you a plan that's not quite as good, but then execution will be a bit longer, but overall you could save time, so maybe that's a better idea. Another possibility is to do periodic replanning, to derive very, very quickly a plan that may be even incomplete, or it may be based on a simplified model of the problem. So when you execute it in the real world, it's more likely to fail, but that's not the end of the world. If you fail, you can do replanning. And these kind of problems can save time further in terms of completion time. The most interesting piece of work that we have worked on involves continual planning. It's an interesting idea where you have a planner that is working on a plan, and immediately after the planner starts, when there is no plan yet, you start acting. But you need to decide, for example, if I want to go back to the computer science building, I can just walk towards the door. It's a pretty reasonable first approximation. And for a robot, it may take 30 seconds to get to the door. By that time, you can find a plan for the next action and so on. There are some very interesting questions about how to do that, and the most interesting ones are how to take a regular planning algorithm, there are many that were developed, and without changing it that much, use it in a continual planning paradigm. And we managed to do that, where the only caveat is that what has been done has been done. You can't allow the planner to change actions that were already executed in the real world. You can't go backward and say, I found a better action, and the first thing you need to do is not to exit through these doors and maybe go somewhere else. So we need to take that into account, but through some simple bookkeeping, we managed to do that. The next challenge that is an important challenge in AI is the fact that in many cases, we need to build systems that act based on uncertain information. They need to act based on beliefs. Instead of knowing for sure their location or whether the package that needs to be delivered is placed in a particular room and so on, there may be uncertainty about lots of these things. There may be ways to reduce uncertainty, but not to eliminate it altogether. So the setting is that you have a robot or an agent that is taking actions, but after each action, it doesn't get perfect information. It gets some imperfect information. It can update its belief using that information. There's been a lot of work on how to consistently maintain beliefs based on what you had before and the new piece of information without necessarily keeping too much data. But one of the challenges is how to act based on these beliefs. I want to show you a short clip prepared by my student Kyle, showing a robot navigating from a starting position to a goal state, where on the top right, you can see the beliefs of the robot. This particular robot can only update its beliefs by touching walls. That's the only feedback it can get. It doesn't have a GPS, and it can confirm its location by touching walls. The dark blue represents more likely states, the lighter blue, less likely states, and you can see that it's managing to find the goal, even though it has uncertainty about where it is, and it can find the best action. In the next example, the robot starts without knowing even where it is. It's being placed, it's like being picked and dropped into the environment. So there is even more uncertainty initially. You see this, the blue locations are scattered all over, and it needs to deal with that kind of uncertainty. But over time, perhaps not being as efficient this time because it didn't know initially where it was, it manages to find its way, and as you can see, I think there is an example there where it's trying to touch a wall, but there is no wall, or maybe we missed that. In any case, it's confirming the existence of walls or the lack of existence of walls, and it does that sometimes twice to be sure, because all that is not very reliable, and it finds the goal. So the model that enables this kind of reasoning is called POMDP, or Partially Observable Markov Decision Process. It's an old model that was introduced in 1965. The first planning algorithms for POMDP was introduced by Sondig in 1971, and it wasn't a very practical algorithm. It had mostly mathematical significance. There was a resurgence in interest in POMDPs and in algorithm development in the 1980s, when it became the foundations, or part of the foundations for AI planning and reasoning under uncertainty, and also part of the reinforcement learning representation. I just want to mention a couple of contributions that we made over the years. My former student, Eric Hansen, introduced the first policy iteration algorithm that represented policies as finite state controllers. And another student, Christopher Amato, introduced the first algorithm that optimizes finite state controllers using some techniques that's based on nonlinear programming that turned out to be quite efficient. Today, there are several efficient algorithms and numerous applications of POMDPs in AI, or robotics, networking, medical diagnosis, drug discovery, and many other areas. I'm not going to go over the details of this, but just want to mention the nice thing about the NLP approach is that it involves no programming. You encode the problem in a certain language and submit it to a standard solver in the cloud maybe, and you get back your plan. So that's an attractive property. In 2015, I started a collaboration with Nissan Silicon Valley Research Center with the goal of addressing the way autonomous vehicles handle intersections. It was only natural for us to think that perhaps we can apply POMDPs to this problem. POMDPs were not applied to a problem of this scale. We wanted to produce a general solution to the intersection decision problem, meaning situations where you have N-way stop signs, traffic lights, T-intersections, uncontrolled left turns, right turn on red, crosswalkers, jaywalkers. It's a very hard problem. What makes this problem hard, and it is one of the hardest things that autonomous vehicles need to grapple with. The right-of-way requires monitoring of the arrival times of other vehicles and can be ambiguous. A vehicle that has the right-of-way could be blocked by a pedestrian or bicyclist, and in which case somebody else can take a turn. Entities can convey beliefs or intentions via actions like edging into the intersection, or signals like blinkering. But the hardest thing of all for us was the fact that the number of entities that needs to be monitored, detected, and interacted with by the NV is really not just very large, it's not bounded. Any person that arrives in the environment and wants to cross the street needs to be accounted for. And factoring all these entity configuration into any possible model of an intersection seemed to be totally impossible and intractable. So we came up with a solution. This was largely the PhD work of Kyle Ray, who is somewhere here, who filed his thesis last week, where we decomposed the general interaction between the vehicle and all these other entities into many different pairwise interactions, each one of a certain type that we could identify ahead of time. It wasn't a specific vehicle, it was a type of problem, a type of interaction. Like the interaction with the vehicle that may come from the left, or the interaction with the pedestrian that may cross the street in front of you. And for each one of those, we created a decision problem, a model that represented the situation as a POMDP, and we solved it offline. When you solve it offline, you can either generate a plan for a specific situation, or in planning, you can sometimes generate what's called universal plans, plans that are good for any possible starting state in that particular space. So we created complete plans for those decision problems. And what happens in real time is that the vehicle is approaching an intersection, it detects entities, and it instantiates a decision problem and with the right parameters, and those are called decision components. Each one of these reasons about what the car can do safely from its perspective, and it makes a recommendation to an executor that needs to solve the entire problem based on some principles like minimizing regret, which in AI means what is the largest possible difference between what you're going to do and the best possible action in that context. So this is just a simple example or visualization of part of what this POMDP reasons about. There is an autonomous vehicle approaching from the bottom. You can see how the intersection is segmented into discrete areas where it's the area where it's approaching at the intersection, edged into the intersection, inside the intersection, and goal is basically past the intersection. There's another vehicle coming from the right, and in this heat map, you can see a representation of the belief that different states associated with the autonomous vehicles are blocked by the path of that vehicle. We're not even sure if that vehicle will continue straight or turn left or right. There may be some beliefs about that, and so on. So these are the kind of beliefs that POMDP needs to reason about. The overall system is summarized by this diagram. Again, we have a library of decision problems that represents various interactions between an autonomous vehicle and different entities. And we instantiate them. In this case, we have 2 cars and 1 pedestrian. And each one of them tracks a particular entity in the real world and recommends a safe action from its perspective. And in this case, 2 recommend stop and 1 recommend goes, and the executor decides to stop, fortunately. In this clip, we can see Modia in action. This is actually an experimental autonomous vehicle that runs our code, approaching an intersection. On the top left, you can see a schematic view of the world the way it's seen by the autonomous vehicle. And on the top right, you can see the symbolic representation of the instantiated decision component as they are instantiated, what actions they recommend, what beliefs they have. It's just partial representation of that. Overall, Modia was shown to produce more efficient and more natural autonomous vehicle behavior than the previously developed approach, and it is subject of numerous patents that were filed by Nissan that includes our UMass team. We really hope they're going to sell them soon to another car company. And I believe it's certainly one of the most complex and largest problem that was solved using POMDPs. There are many challenges that remain that we work on right now. Recognizing and reasoning about the goals and plans of other agents in a more explicit way. Communication with others using signals and gestures. Broadcasting the intent of the AV, which is generally recognized as a good idea, so that when an AV approaches a crossing, it tells the person who is crossing that it noticed them and it's safe to cross. For example, there will probably be various kinds of indicators for that. Handling more complex types of occlusions and unexpected obstacles, learning competence models and the boundaries of safe autonomy, and deciding when and how to seek human assistance. We have now a couple of projects funded by NSF and Nissan that are looking into all these questions. They are hard questions. I want to switch gears now and talk about the problem of interacting with others in the context of a system that has multiple agents. The challenge is how to achieve intelligent, coordinated behavior of a group of decision makers in spite of stochasticity and partial observability. And perhaps the most important part that made this problem hard is that we looked at situations where each agent has its own sensors and its own streams of observations, and its beliefs about the world are going to be different than the agent that it's maybe collaborating with. And there isn't enough time to share all that information and form a shared view of what's happening before you take the next action. We're looking at the decentralized decision-making where each one must decide based on what they know. Communication may be possible, but it takes time, and it cannot completely eliminate that need to operate based on potentially misaligned beliefs and partial information. To study these problems, we created a new model that extends POMDPs, and we called it Decentralized POMDP, or DEC-POMDP. It's the model that Laura mentioned was recognized by this influential paper work that we will be getting next month. And it really became a standard in the field of multi-agent system for studying coordination from a decision theoretic perspective. In this model, we have multiple decision makers. In this case, we see two, but it could be more. They take actions that modify the world, but each gets their own private observations. In this particular case, we have only one objective, so they're all working in a collaborative manner and share the same objective. In other contexts, they may be competing and have private objectives. We study some of that, in which case it's called a partially observable stochastic game. The first set of applications that we used that motivated this work included a project by NASA that was designed to study possible cooperation between space exploration rovers. We also looked at some communication problems in networking, like what should two nodes on a network that send a message do when there is a collision, and this problem is solved using some heuristic methods, but we wanted to see if a decision theoretic approach could give us a better answer to that. What are two robots supposed to do when they try to do something together, maybe even just to meet as soon as possible, but there is uncertainty about the rate of progress and where they are. And we also looked at some problems that were inspired by the CASA project of how to coordinate in real time multiple radars that are tracking some weather phenomena like tornadoes. Each one can scan only in one direction at any given time, and it needs to be coordinated in order to create a good reading of the phenomena that they're tracking. The models we created extend MDPs and POMDPs in ways that we characterize theoretically, but one of the interesting things was that one version of the problem that we called decentralized MDP was a situation where we have perhaps just two agents. Together, they have perfect information, but it's split between them. One sees one part of the information, the other sees the other part of the information, but they have perfect information. They just can't share it all the time. They can even share it through communication, but not instantly. It turns out that that problem is as hard as the problem of not having perfect information, and that was a little bit surprising, and it led the graduate students who worked on this to conclude something that I never fully understood or agreed with, but I think he's right. He said that decentralized decision-making is more complex than dealing with partial observability in some sense. But we derived, and that was the work of Dan Bernstein, we derived some theoretical result about the complexity of decentralized POMDPs using some In computer science, just for those of you who are not familiar with these, problems belong to different complexity classes. And generally, there are certain classes that are generally accepted as practical, and if you belong to another class, first it's clear that you cannot find an optimal algorithm, or you cannot use an optimal algorithm to solve that problem. And sometimes you can even prove that approximation, bounded approximation within a certain precision cannot be accomplished within an acceptable amount of time. So these results provide some guidance for designing algorithms. And what we showed is that decentralized POMDPs and decentralized NDPs with just two agents belong to a complexity class that is called next part, which in practice means that they're double exponential. Usually exponential complexity means impractical, so these are double exponential. We could have just finished all the work on this with that result. We published it in a journal and we could have said nobody can do that, and in fact that's how many people felt for a number of years. But the real world has a lot of added structure. It turns out that a lot of problems that inspired this work are not next part. People didn't realize that there is additional independence or structure in the world that makes the problem easier to solve. And understanding these structures and seeing how to design algorithms that exploit them is a very important thing. One of the early problems we worked on, just as a toy problem, was called the box pushing problem, where two robots needed to push boxes to some target area. There were small boxes where a single robot can push, and there were larger boxes or heavy boxes that two robots need to push together. And it was one of the early problems that, again, this kind of problem of this size cannot be solved optimally on the best computers. But we could design algorithms that can give us good approximations. We call that algorithm memory-bounded dynamic programming for DEC-POMDP. And my former student, Chris Amato, implemented that on a real robot, and I think that that was probably the first implementation of the model on a physical system. He actually built these robots or used these robots and programmed them to use these planning algorithms in order to push boxes to a target area where they don't know where the boxes are, and in this particular case, example, they cannot communicate. They need to coordinate just by reacting to what they see. And you can see that the white robot is waiting behind the larger box, and the green one is looking for whatever work it can do, and at one point it may find that there is this box that it can push. Chris looked at a variety of versions of this problem. Here it is, successfully pushed to the target area. He looked at situations where the robots can use communication, and he looked at situations where there may be very limited communication, maybe just a signal saying, I need help. Maybe they can raise a hand. And one of the nice things about these algorithms is that if you provide them with very limited communication bandwidth, maybe just one bit of information, part of the algorithm is to decide, part of the planning process is to decide how to use it in the best possible way. What meaning should be assigned to that? It doesn't need to be predetermined. And in fact, at different contexts and different times, it could have different meanings. Over time, we looked at the whole range of problems, and we established the fact that some problems have certain independence relationship or other properties that make them easier, not just NP rather than next part, but also polynomial, and created a whole taxonomy of problems like this one. And overall, this body of work answered some fundamental questions about decision-making in a decentralized setting, the complexity of the problem, how the complexity varies with certain characteristics and features, whether it's possible at all to solve these even small instances optimally, and how to make dynamic programming techniques practical for these problems, how to use communication in this framework, and how to create scalable algorithms for that. I think the reaction of most of the community to POMDPs when they started was, hey, that's a rich model, very elegant, but it's not going to be ever practical. And now POMDP algorithms can be used for quite a lot of practical things, including to control autonomous vehicles. In the case of decentralized POMDPs, the reaction was similar. And again, we see now how they can be used, at least for strategic decision-making, by multiple agents. But the main message that I have is that the real world is like that. It's not like we invented a problem that has this complexity and, hey, let's not deal with it because it's too hard. The real world is like that. We have multiple agents that cannot share all their information all the time, and we want to be able to do planning effectively in that context. This is one of the problems, one of the first problems that we managed to create plans that involved dozens of agents. A lot of the early work just involved 2 or 3 agents. But today, these algorithms can be applied to situations that involve dozens of agents and to figure out decision-theoretic versions that have good properties and can maximize performance in the context of, in this case, a sensor network. So what is missing? Today, AI is having a tremendous impact on how we live and work. It is changing many industries, from drug discovery and healthcare delivery to transportation, finance, and security. Some predict that we are at the cusp of another industrial revolution. But for me, AI is not a technology. It is first and foremost a science at an early stage of development with many fundamental questions that are unanswered. In 1995, Marvin Minsky said, almost any error will completely paralyze a typical computer program, whereas a person whose brain has failed at some attempt will find some other way to proceed. We rarely depend upon any one method. We usually know several different ways to do something, so that if one of them fails, there is always another. So we need to make AI more robust, a lot more robust. We need to be able to deal with incorrect models. Our models are always going to be incorrect. No matter how much data and how much effort you make in creating a model, there are not going to be any models of the complete real world, except for physics. Physics is the real model of the real world. And we may need to resort to that. We need to deal with misspecified goals. If you tell your computer, Siri, I need to free up some disk space, you don't want the computer to delete some of your important files. We need to deal with human user error, with cyber attacks, and perhaps the hardest of all is with unmodeled phenomena. And autonomous vehicles will have to deal with unmodeled phenomena, what some people call the unknown unknown. There is a long way to go. If you look at the way some computer vision and machine learning algorithms fail today, it's quite baffling. This particular program recognizes animals, and on the left, it recognizes a panda correctly. Now we add some random noise to the image, and we get the image on the right, and a person looking at it still sees a panda. It's actually very hard to see any difference. But the machine learning algorithm now recognizes it as a given with 99.3% confidence. Maybe more troubling is that these defaced stop signs cause the machine to recognize them as speed limit 45. And the last one was recognized as a stop sign. There is a whole area in machine learning right now, adversarial machine learning, that is trying to deal with these issues. Some of these issues are not because of an adversary, but now think about some real adversary that is placing sign in the environment to fool an autonomous vehicle. Right now, it's extremely easy. So to be robust, AI needs some common sense. What is common sense? Generally, it's a bunch of everyday facts, like birds can fly, that all humans are expected to know, even though there are exceptions, like penguins don't fly. And that's okay, we can deal with those exceptions, with the fact that the facts we reason with are imperfect and so on. In general, common sense is what you use in order to determine that the socks that you placed in the drawer today are likely to be there tomorrow. But the chocolate bar that you placed on the kitchen counter is not likely to be there tomorrow. That's common sense. AI doesn't have common sense. An autonomous vehicle needs common sense for a lot of reasons. They need to be able to figure that a plastic bag in front of the vehicle can be ignored. But is this puddle too deep to cross? Is this policeman telling me to stop or just to slow down for a minute? Or maybe he's gesturing somebody else? Is it safe to drive over these power lines? And is this passenger waiting for me, particularly at the airport where there are dozens of them and dozens of cars to be matched with? The first AI program to address common sense was Advice Taker, written by John McCarthy in 1959. And these efforts continued over the years with some very ambitious projects like the Psych Project. Paul Allen, the co-founder of Microsoft, announced last year an investment of $125 million for new common sense AI. And DARPA has new programs designed to teach AI some basic common sense. These efforts continue, but I think I can safely say that they have not reached the common sense of a 3-year-old child. So I want to conclude with a quote from Donna Strickland, who received the Nobel Prize for Physics last year. She said, "Scientists need time to make discovery." I think that AI is a modern science, and when it comes to understanding and replicating human intelligence, we're still in the dark in many ways, and there is a long road ahead. And maybe it's a good thing. Don't trivialize human intelligence. And with that message, I want to thank you again and open it up for some questions.
Professor Silberstein, it is really my great pleasure to present you the Chancellor's Medal, which is the highest honor bestowed on any faculty member on the Amherst campus.